Hello and welcome everybody to another webinar here at Fronius International. Today I have the topic fire safety of PV systems with me. Now before we head on in today's topic, I quickly want to introduce the team consisting of Michael Raunig. He's behind the camera today and answering your questions, which you can send in via chat. And myself, I'm Christoph Schierlinger, also part of team training, and will guide you through the next 20-25 minutes of presentation. Now, as mentioned, if you have questions, don't hesitate, send them through. We will take time afterwards also to answer a few of your questions live. Now, today's topic is, of course, very controversial, as you can imagine. PV fire safety. Is it safe? Is there a potential source of fire? How high is this risk of fire? And I have brought with me today a few case studies. The first one is from Germany, and they were conducting this around the question, are PV systems a potential source of fire? And between the year 2000 and 2013, they looked at 1.3 million installed PV systems in Germany, and they found out that there have been about 430 fires or heat damages, which is about 0.03% out of these 1.3 million. However, keep in mind that only 210 out of these were triggered by the PV system itself. The other fire damages were just simply because a building is burning and, of course, also the PV system burned down. Now, with these 210, we were talking about 0.016%. So, in other words, we have a safety factor of 99.8%. 99.8% of PV systems are safe. There is no fire issue. There is no hazard. So in other words, we could say that PV systems pose no health, safety, or environmental risk under normal operating conditions. Now, of course, I don't rely on just simply one case study. I also brought with me another one from the UK. It's a little bit earlier, so in 2017, from 2010 to 2017, they conducted this survey. They looked also upon 1 million systems in the UK and found out that about 58 fire incidents happened during this time, which gives us the number of 0.0058%. So even better. Now we're talking about a safety factor of 99.99%. So all in all, and again, we are talking about a very safe source of energy with photovoltaic systems. So in this case study of UK, they did a little bit deeper digging, and they also looked on which type of error did occur. And as we can see here with the green part of this cake, nearly 50% happened in the installation section. So installation errors did occur. And when you look even deeper, they found out that the components causing this fire are mostly related to the DC side. So we see here external DC isolators, DC connectors, DC cables. Now, we already can see DC is the most hazard or the highest risk that we can come across here in such a system. And this is also the part where we focus on in the later slides. Now, just for fun, a quick comparison also in terms of fires now related to the Christmas time. Only in the Christmas period, we are talking about 10,000 to 11,000 fires compared to, what did we have again? 16 fires a year through PV systems. So I would argue that it is much safer to have a PV system on the roof than a candle on the Christmas tree. Or in other words, again, there is no, it wouldn't be wise to decline the offer for a PV system because of fire hazard issues or the worries about fire. It is more there's a higher safety than with the Christmas lighting, for example. Just as an example here. I have a little bit more facts and figures with me. At every point in the footnote, you can see the reference. So if you're interested, you can also check it out yourself and do a little bit of a deeper digging. Now, for some others, we have Netherlands and Italy. They also did such surveys, and all of these surveys have similar findings. And it's mostly about the most frequent causes of faults, which are installation errors on the DC side, as mentioned before, and mostly on DC connectors. So this is the part where we now head on into the next chapter. Before we do that, one quick statement from TÜV Rheinland and Fraunhofer Institute. They said each piece of electrical equipment bringing a new connection into the system poses the risk of an electric arc. So our main goal, our highest goal should be when planning a system to minimize the number of DC connectors or DC plugs in such a system. So go for a lean, for a simple system. That should be the goal. All right, so now we have heard that DC connectors, the DC MC4 plugs mainly, pose the highest risk when it comes to fire safety. Now, what could be defects? What could be common issues with those plugs? We have two pictures here. On the left-hand side, we see a correctly crimped MC4 connector with the correct tool, optically perfect, and we can also see that the pull-out force for this plug is on about 455 Newton, and the IEC standard demands at least 310 Newton. So plenty strong for our standards. Now, on the right-hand side, we see the opposite, wrong tool for the job and not the correct amount of force for the crimping, and therefore we have a pull-out force of not even 100 Newton. And yeah, you can imagine what this could lead to. You simply, or it is much more easier to pull out the plug from the cable itself, and therefore an arc could occur. Now, I have listed down below some of the most common defects. We have heard now of poorly crimped plugs. Also, a very high risk is connecting different plugs of different manufacturers to each other, because as you can imagine, different tolerances, different materials, different thermal expansion rates, and therefore there could be an arc occurring. Number 3 would be corroding due to weathering. For example, the gasket couldn't be sealed properly because I didn't torque it enough, the sealant. Or last but not least, the plug is not fully inserted even, so we didn't hear the clicking sound. Could be a most common defect as well on these plugs. Also, the IEC standard has its own declaration in the norm, and it says male and female connectors mated together shall be of the same type from the same manufacturer. So keep this in mind, because as mentioned before, we could have different materials, different aging, thermal expansion, and even if there is just 1/10 of a millimeter distance between connectors, this could lead to a microelectrical arc, which could lead to fire in the worst case scenario, which could be not covered by insurance or product warranties. And to showcase that this really is a big deal, Stäubli Group, or previously they were called Multi-Contact, they did a testing with their own MC4 connector, the Stäubli connector, to different MC4 connectors out in the market. You know it, there are hundreds out in the market and they all claim to be MC4 compatible, but some of them are not, simply. They are not compatible. And this picture very drastically shows us what can happen there with the thermal imaging. We can see that there, in the worst case scenario, there is up to 97 degrees Celsius temperature increase because of incorrect mating here. So we do not want that, of course. Yeah, because if we do that, we could have this instead with a melted MC4 connector, even a burn of the MC4 connector, and yeah, this could lead to a fire. All right, so let's put this to one side. This is chapter 1, the DC connector. What we have heard is it's very crucial to go for a slim installation, for a slim design with the amount of DC connectors that we have, and go for the same manufacturer for the same type of MC4 connectors. Do not mix up multiple ones in such a system. Now, in chapter 2, I now want to lay the focus onto DC optimizer. Now, of course, it's all well and good if you have a shaded scenario and you can rely on a DC optimizer system to bring out the best in such shaded scenarios, even though there are systems out there performing just as well without optimizers on them. However, some of the DC optimizer manufacturers claim that they are even safer, their systems are safer, because you can shut down on a module level, which of course sounds very, very good because you have an increased safety for firefighters in case of emergency. But is this really the case, is my question now. If we compare two systems, let's go for a 6 kilowatt peak system with 20 modules and compare it with a DC optimized and standard modules with a string inverter, we simply by counting come to the conclusion that we have 3 times the number of DC plugs compared to a standard system with a string inverter with, for example, the Fronius. Now 61 plugs versus 21. And the conclusion should lay on hand. This is controversial in itself. We have a component claiming to be safer in case of emergency, in case of fire, but in the beginning we have a higher risk of fire because we triple the amount of DC connectors. So this shouldn't be the way to go for in the first place, in my opinion. Why not go for a simpler solution for a lean system, as we have mentioned? Also, we have a report here, or a statement in a report from the IEC. They have a report on fire protection measures here. And the statement in there is saying the application of these measures, with these measures they mean the DC optimizers, may increase the number of contacts from relays or connectors, which may increase the risk of fire. So this should be considered in fire prevention considerations. And this statement comes from an independent international standardization organization. So this should mean something, right? And what better way to showcase it to you than with an example? We have here Project Titan. This is in the USA, and Project Titan is simply the project name for it. They mounted several systems, PV systems, onto Walmart stores. And all of these systems had DC optimizers and DC plugs from different manufacturers on them. Not a good idea, because what was the result? On 7 of these Walmart stores, they caught fire. They had fire hazards. And some of these burned down, with the picture on the right-hand side. And one more follow-up for them to do was to exchange all the incompatible DC plugs later on. So even more money and time invested into it. So what do we learn by that? Probably not a good idea to mix the MC4 connectors. And if you look at the picture, it is a simple east-west installation with a slight inclination. There would be no need for a DC optimizer there. A standard system would do the trick as well. So yeah, this was an incident in the USA called Project Titan. And this could be a picture as well. So optimizer and safety, yeah, doesn't look that safe anymore. And one more thing I wanted to add. A DC optimizer has the same standards, the same ratings to fulfill than a Fronius inverter when it comes to ambient temperature, for example. So both have an ambient temperature of 60 degrees where they have to work in. Now, no one can guarantee that in the case of fire, when this thing starts melting, that this is also possible to shut down the module. Because in the case of a fire, we have more than 60 degrees ambient temperature, far more, and therefore this probably cannot fulfill or may not fulfill the shutdown anymore. So another thing to take in consideration. One way to supersede these thoughts would be to go for a software solution, for an algorithm that we at Fronius call Fronius Arc Guard. The Fronius Arc Guard is an algorithm. It's a precise detection of serial DC arcs. And when we detect them, when we measure and detect them, we shut down the production and therefore we extinguish the arc. It's a very simple measure, but a very effective one. And it's also a trained algorithm or a self-training algorithm for a continuous improvement. Now, we have a lot of experience at Fronius with this topology. As you can imagine, in the perfect welding since 1950, we want to create very steady DC arcs. And now in the solar energy, we want to prevent them. And what easier way to go for than to use this experience in order to detect them. So this is the way we went here and we created the Fronius Arc Guard. Now, in the near future, all of our products will be equipped as standard with these solutions. Some of our products are already equipped, like the Fronius Simo Advanced. Also some options and variants of the Tauro product. And the Gen 24, like it is hanging behind me, will be equipped by standards by end of the year roughly with a new rollout. And then all of the product series will be equipped with this solution. They can be easily activated via the user interface. Now let's conclude chapter 2 as well. More system components and more DC connectors lead to a higher potential for an installation failure, which can lead to a fire. And our recommendation now, in order to prevent this, are the following. Go for high quality of installation. It is crucial for the safety. So when crimping, when deciding which cable to use, which component, which module, which inverter, really go for the high quality installation. Go for a minimum number of DC connectors. So simple solution, a lean solution. This should be our main goal, our highest goal. And also check for quality of components. As mentioned before, do not mix the different MC4 connectors. Go for a high quality and use both of them on male and female side. And this even goes down from module to inverter. Go for a higher quality, then you also have a higher safety. And what you can also think about is a periodical maintenance of the PV system. This can range from a simple optical check underneath the modules if the cables are still attached to the module and are not laying flat on the roof. If there is any visual open cuts on the cable isolation, for example, you can do isolation measurements, or you can go for a optical heat camera and do a scanning of the PV generator. So stuff like this could be done as well. Now, I want to end with a statement here again from TÜV Rheinland and Fraunhofer Institute. Every additional component carries the risk of additional contact points and other sources of error. A lean and simple system with as few components as possible has the advantage that there are fewer points where damage to the system can occur. Now, as mentioned before, we want to go for a lean, for a simple system. That's the goal. Yeah, last but not least, one example, one reference even, the gas station operator Total is now currently equipping up to 5,000 of their gas stations worldwide with Fronius inverters, which is leading up to a total output of up to 200 megawatts. And they decided to choose Fronius because of the high safety requirements and our robustness. All right, that's it for the webinar so far. Thank you very much for listening. What comes next is, of course, the recording will be sent out to you. You can expect it in the next few days in your email, and you can rewatch it as many times as you want. Also, in the following week, we will upload it onto YouTube. Then you can share it with your colleagues as well. If you're interested in the studies that we have seen, you can also search for them on your own. You have seen the footnotes in the presentation. You can do that as well. More information on your homepage. Not a problem to register for another webinar and online training, or we are also very happy to welcome you here on site in Wels for a face-to-face training. Now, that's it so far for the webinar. If you have questions, just keep them coming. We are happy to write you back, and thank you very much again. Have a nice day and see you next time. Goodbye.